explosive in the door or something.
Here, put this on top of that.
That's good.
Nobody can do it. Maybe you can just pick it.
That's good. Thanks.
Sure, why not, right? We can pass something around.
Alright.
Thanks.
What do you have? I'm not going to take your
Alright.
I'm going to take out my douche paper, man.
Are you going to just like make it? You guys ready?
No, I'm going to go with
Almost.
my pronounce right? Yeah, but I can't pass around a cooler.
I'm getting nervous.
I mean, not as quickly.
Oh.
Alright.
Thing with
Let's
stuff on
do it, I guess.
It's the little black box. Yeah. You want to stand up there, just back up down? Alright, so, what do you guys think is going on over there? So, I won't make you guess, but there's a...
Good guess, man.
It's learning. Water, Helen. So there's this is a page, right? Someone just took a picture of it, and this is the text. So it's kind of reading this thing on its own from the picture. So there's a lot of cool thing that got me into this stuff is there's a lot of stuff only people could do before that now computers can do. So everyone's familiar with this. This is Netflix recommending movies to you, like it knows you, like it's your friend. So that's another application. And anyone know what this is? Any people? Yeah, someone else want to explain it because I already explained it to everyone, including like my grandma and stuff. So anyone? Go ahead.
That's Google's deep dream thing. So Google has neural nets that recognize images, or they recognize things inside images. So they can set those neural nets up so that when it thinks it recognizes something in it, it can kind of like enhance it in it. Maybe
Sort
I'm
of.
not explaining it
I
well.
mean, I don't totally get it, but it's just like they had these big nets that, or they had these complicated algorithms that recognize images, and they basically slapped one of them until it made images, and now they fed it this image, and you can see there's like castles on here that there weren't before.
It looks for
crazy shit going on.
It looks for like curves that match. I mean, this looks like Chinese architecture or something.
Yeah.
That's or Japanese architecture. It looks for in the original image stuff it thinks that might be that, and then every little bit makes it a little bit more like that. So it finds all the things that most resemble Chinese architecture and then makes them more resembling Chinese architecture or Japanese or whatever Oriental people have seen.
Yeah, so this is pretty cool. This came out like this summer. Probably couldn't have come out 10 years ago. So this is new technology. This field is kind of exploding right now. I think it's kind of exciting. And of course, they can also predict the prices of houses. That's pretty cool. People can kind of do that. But the reason I'm put up this bad image is because the example we're going to stick with to sort of explain the ideas is we're going to take the sizes and numbers of bedrooms and things like that, statistics about houses, and we're going to predict how much they cost. So that is something a person could do with a lot of training or maybe after looking at a lot of data, but no one wants to do that. Everyone wants a computer to do that. And we'll talk about how to get a computer to do that in a second. So that's a robot, this little picture of a robot. And what is machine learning? What's the difference between a machine learning algorithm and a regular machine running algorithm? So the difference is the ability to learn without being explicitly programmed. What does that mean? Well, if you were going to teach a computer to, say, recognize characters, like that first picture, you would probably go in, you'd have to write a really complicated algorithm for the 4, like you find the lines and make sure they're aligned the right way, and another complicated algorithm for the 6, and you'd have to go on like that. But basically what you would be doing in the end is you're looking at the pixels with your eyes, right? And you're taking in the information stored in the pixels and you're computing some kind of function of that information. So the input is the pixels and the output is the classification of the written thing as a digit or a letter or something like that. So basically, machine learning says, what if you didn't have to do all that work of figuring out which function to compute? What if the computer figured out which function to compute and then computed it too? So we're just sort of outsourcing higher and higher levels of our mental functioning to the computer. Does that kind of make sense? What's up?
Are there different kinds of machine learning algorithms?
Yeah. Okay,
Or
so
a few slides.
general categories. Supervised learning, that is the example of the character recognition or the, what's the other one? Or the housing thing is supervised. That means basically we know what we want. So maybe we want to know what numbers on the screen. We want to know whether there's cancer or not in this image of a cell. And we have labels. So labels are pre-classified data, right? So we know what the truth is, and we are trying to find a model that will predict the truth. As opposed to that unsupervised, you have no labels, you're just looking for sort of general structure in the data. So an example of that is the Netflix thing. So you don't know what someone's gonna like, but you sort of build a model of, okay, so let me go into that a little. Unsupervised, shut that, yeah.
Yeah. Laying down the law.
Woo!
No machines.
Only learning.
Yeah. So unsupervised could be clustering, which is basically separating the data into a predetermined number of groups that it makes sense for them to be in. Or there's a thing called the latent variable model where you discover variables that are not necessarily explicitly in the data, but that you think might be influencing things, or the machine thinks might be influencing things. So that's how Netflix works, for example. They have an algorithm that comes up with its own sort of categories. So a person might think action or adventure, or this person likes romance or something. And Netflix sort of comes up with its own latent, so it's not clear to us what they mean, but Netflix has its own axes that it puts movies on, that the machine discovers on its own. I didn't go into classification and regression, but basically, supervised learning, we're generally trying to predict something that we know is, okay, we're generally trying to predict something, and classification is when we're trying to classify something, so we're trying to predict maybe, is it cancer or not, is it a 1, a 2, a 3, a 4, or a 5, and regression is when we're trying to get an estimate of a real quantity, like predicting the price of a house. So there's too many prices of houses to make a little category for all of them. So regression is more of an estimate. Well, you get it. Is that clear? Any questions? Okay. Moving on. There's a lot of them. So that picture is from Scikit-learn's website. Scikit-learn is a popular library of implementations of machine learning algorithms. And it's kind of a flowchart. Hey, come on in. It's kind of a flowchart, and you start there, and it tells you, like, if you have this much data, or if you're doing this type of task, go here. And all of these green things are not even single algorithms. They're like general categories. So this is a huge field. It's a new field, but it's already huge. So we're going to get a very, very general overview today, if that makes sense. So this is just like a sort of look how big it is type slide. No real information here. Terminology. Okay, let's get into the real stuff. So there's a few things we'll be dealing with that we're going to need words for. First one is examples and labels. So pretty self-explanatory. An example is a piece of data, like a house, an image, a cell. Labels are, well, like I already mentioned, it's what we want to predict. Is that clear? Everyone get it? Okay. So training set and testing set is important. We need to show our algorithm a lot of data in order for it to get a good idea of what's going on. But then we also need to know how well it's doing. And we can't check on the training set, or we can't check on the data we already showed it, because it kind of is already biased towards that data. So we need to show it data it hasn't seen before to figure out how well it actually knows what's going on. in real life. And the way we do that is we separate it into a training set, which is usually most of the data, and that's what we train the algorithm on, and the testing set that we then validate it on. Features are going to be the things we know about the data, like maybe the numbers we have, like number of bathrooms, or in the case of, what are the other cases? In the case of character recognition, it would be pixels. So features are what you know. So for each example, there will be one number for each feature. Does that make sense? Parameters, what our function depends on. So what are we trying to learn? I'll get back to that. The cost function is really the sort of important thing here, because the cost function is the connection between what you want from the algorithm and what the algorithm is going to give you. So your cost function that you come up with represents what you want. So what do I mean by that? What I mean is, if you want your algorithm to recognize characters, you need to be able to figure out how good it is at recognizing characters and then make it better. So you need to be able to measure how well it's classifying characters right now. And the way you measure that is with the cost function. So it's kind of pessimistic, right? It's not how good we're doing, it's how bad we're doing. It's what the cost is. And then the way we make our algorithm better is by sort of finding the parameters where the cost function is as small as it can be. Any questions? That might have been a little loose.
So cost is like how much information you're losing along the way?
Cost is like the error between your predicted answer and the true answer.
Okay, so the cost is, this isn't a specific function, right? So this is a general category, so it could be how much of it are we misclassifying? It could be how far away are we from the numbers that we want, right? For unsupervised algorithms, it's going to be something else. But the general idea is it's the function that plays the role of how well is my algorithm performing.
Could you explain what some of the labels and features might be, like a house?
Sure.
I think when we do linear regression.
Oh yeah, I'll go through what the features are. So in the case of predicting the price of a house, or you guys could do it, I mean, what are the examples and labels? So each example corresponds to, in real life, a house, yeah. And the label of the house is what we're trying to figure out, so what's that?
Price.
The price. Training set, testing set, just however we divide that. So what are the features then? What might some of the features be?
Yeah, square footage.
Yeah, square footage, anything else? Location, absolutely.
Number of bedrooms.
Yeah,
Yeah.
number of bedrooms.
Number of bathrooms.
Anything like that. Anything that we're actually paying attention to about the house we'll consider a feature. Sometimes features aren't even real, they're like other stuff that came from other algorithms that it figured out, but we're not going to worry about that today. So what are the parameters? You guys can't answer that yet, so let's move on.
I was going to say, I'm excited for that answer, please.
Yeah, so should we do what's the cost? No, we're going to define the cost function.
Yeah, well, I mean, yeah, there's a whole...
Oh, hey, that's already on there. Okay, so whenever you want to take over.
Okay, so just a really quick example of how we go from talking about, oh, I'll apply a linear model and I'll take features and I'll compute a cost. How we go from there using machine learning to a program that predicts a cost, right? So we already talked about this. The label is the price, because that's what we're trying to predict. We talked about features, square footage, number of bathrooms, distance to the nearest school, anything that you could suppose. I mean, you can picture that the more features you have, you know, your algorithm could get better or worse depending on the features you pick. You might pick a feature like, you know, number of frozen yogurt shops within a square mile that has nothing to do with the price, and it'll throw off your algorithm. The tuning of the features is something that you could think about. Training set most of the data, testing set the rest, and we're going to assume that it's linear. It might not be, but then you pick a different algorithm and you move from there. So this is just to show how we go from this set of assumptions, which kind of makes sense to all of us, to implementing it on a computer. So there's a lot of math that's going to be going on, and it's very formal, and it shouldn't really bother you. You don't have to like apply this. There's no pop quiz. Just kind of get what's going on in each step, And when you get a problem, when you get some sort of tests or some sort of, any machine learning problem and you decide, oh, okay, I think I want to use linear regression, then just look this up. And then you can start worrying about specifically how to assign what where and which row should be where in C++ or Python or whatever. But for now, don't worry about it. We're going to have our x be our input. It's kind of classic, right? So our x is going to be all of our features. So square footage, number of bedrooms, number of bathrooms, and it's going to be a list, a vector, right? I shouldn't say vector. It's a list. It's a list of information, right? The first item is square footage. The second item is number of bathrooms. Third item is number of bedrooms or whatever, right? And each item has a parameter, theta, that's attached to it. And the theta you don't have to worry about. That's what your algorithm takes care of. Your algorithm is going to tune the thetas so that when you attach x to it, it'll pop out the correct price, right? So the thetas is what your program does, x is what you input, and when you combine them, when you take their dot product, you get, which is just multiplying theta 0, x 0 plus theta 1, x1 plus linear algebra, like basic, maybe, generally, okay. So the dot product, right, theta 0, x 0 plus theta 1, x1, gives you your predicted price. And so now we need to define our cost function, because that's what we're trying to minimize. And so a pretty simple idea of a cost function is just the predicted answer minus the correct answer. It's kind of like the most basic error. But that's going to have some issues with signs and stuff, so we square it to get rid of negative, positive. So now everything is positive, and we have this sign, this positive signed error term, right? And we attach a 1/2 on there because later we'll take a derivative, and that'll make it better.
Is the I supposed to be an exponent, or does that just mean the I?
No, so, right, so whenever I'm putting these in parentheses, because you're not raising it to the power, it's just the ith example.
Okay.
So if you have 500,000 houses, you're going to go through the error for each one. So this is a cost of the whole thing. Because your cost on, like, you might have a really, really great model that fits really well the vast majority of your data, but it really sucks on one house because the guy that's selling that house is just like way off in what he thinks the market price is, and so he prices it really badly. And you don't want to tune your algorithm for that point. So you look at the total cost instead of the cost for each one separately. So that's why we're doing a sum over all of the examples of the squared area to get rid of the signs, and the 1/2 makes it nicer later when we do derivatives and stuff.
So what exactly is a linear regression algorithm trying to do?
You're trying to take the inputs of the house, right? So if you imagine a plot with all of the housing prices and stuff, and you're fitting a line to it. I guess I should mention, any linear model, any line, right? We all did this in whatever, 7th grade, y equals mx plus b, right? You always have that plus b term, that y-intercept. So just by convention, so we don't have to separate, we don't want to do a plus b and then have to worry about optimizing b separate from optimizing theta and x. We take the first element of x to be 1. And then theta 0, corresponding, right, theta 0, x 0, and that dot product, that'll be our b term. So,
I have an explicit b term in the implementation.
oh really?
Yeah.
Whatever. I mean, it's fine, it's the same thing. It just, if you do it this way, you can optimize everything all at once instead of like worrying about it. It doesn't matter. So this is the first algorithm that we're going to use. So linear regression is a type of model. There's lots of different algorithms you can use within linear regression. This is a pretty simple one, and it's called gradient descent. And the concept is that wherever you are, this is an unnecessarily complex 3D representation of what's going on.
That's not a real thing, by the way.
Yeah.
That's just a nice 3D graph of something.
Yeah, this will also never happen. They're always going to be like a big bowl with one bottom, but anyway. What it does is you initialize some point, and this is theta. So you initialize all of your thetas, and it doesn't matter where you start them because your algorithm's going to be changing them. So you could start them all to 0, you could start them all to a random place between 0 and 100, whatever. So you start at some place here, right? And then as you run your algorithm, this is the cost function. So it's trying to minimize your cost function right here. So it decreases theta until it reaches, where the derivative is equal to 0, the bottom of a little well, right? And I mean, you can already see it could go this way and then get stuck here, and that's not as good as down here, but that's a choice that is like later when you're seeing that. That's something you have to do, particularly with your data set. And I'm just going to talk about alpha right now while we're here, because that's a really good graph for alpha.
It's not ready.
But it's a really good graph. I'm not going to have it later.
You gotta explain what the gradient is and stuff.
Gradient's all right, fine. Does everybody know what a gradient is?
Anyone not
Maybe?
know?
Anybody feel no shame? Who cares what a gradient is?
I mean, are we talking about like something like a graphical gradient, like something that's like really concentrated and less concentrated, right? Or is this
Okay, yeah. So
totally
you're
different
thinking of
concept?
like a saturation gradient, where
I
it's like
know what
black
that
at this
kind
end
of
and then it like
gradient is.
fades to white. That is actually it's a pretty good concept of like what the gradient does. But a gradient is an operator in math. All it does is it's a partial derivative, right? So a derivative really with respect to one element, right? So we have theta 0, theta 1, theta 2, theta 3, and so it'll take the partial derivative with respect to theta 0 plus the partial derivative with respect to theta 1 plus the partial derivative with respect to theta 2. Again, this is like the nitty-gritty math stuff that we shouldn't really worry about today. I should just say that what the gradient does is it points you in the direction of most change, right? It takes you from black to white, or from black to light gray, or whatever yeah. So what this shows us when we take the gradient of the cost function is it gives you the direction that you need to change all your thetas in to change the cost function the most. And on the previous slide, it was negative, right? We did minus the gradient, so it's lowering our function. If we did plus the gradient, it would maximize our function.
The gradient's just an arrow that points up the hill on the thing.
Right, and we're taking the negative of it, so we're going downhill. And this is, I'm not even going to go through this. This is math that shows you that when you take the gradient of this, you get this relatively nice thing that pops out, right? But again, if you want to apply linear regression, you can look this up. All this is just the sum of your predicted answer minus the true answer times the input thing that you're trying to optimize at that time, because you go kind of one theta at a time. But the point is that this is now, all along, but this is something that you can program, right? You can implement this. You could also just type in, scikit-learn, right? Just linear regression and then give it all the categories. But if you were going to do it from scratch, this is just algebra. This is something you can program your computer to do. And what you do is you tell your thetas, you go one theta at a time. Remember, those are our parameters, right? So you say, okay, theta 0, I'm going to redefine it as whatever it was before minus the gradient of c, right? And that'll move theta 0 or whatever theta you're talking about a little bit in the direction of most descent, right? So that'll optimize that theta 0, a little bit. It'll make it a little bit better. And then you go to theta 1. And you do the same thing for theta 1. You go through this whole process, you take all these cost functions and stuff, and then you redefine theta 1 to be whatever it was before, 0, whatever you started it at, minus the gradient. So you moved it a little bit, right? And so the only thing on here that doesn't really make sense yet is this alpha. Like, why? What is this, right? And so the concept is that if I have that slope that we were looking at earlier, and I take the gradient and I move in that direction, and I take a huge jump in that direction, I might overstep where I want to be, right? So this alpha is what's called your learning speed. If you make it a really, really small number, then what's happening is you're taking the direction of most change, and you're going a little tiny bit in that direction. And then you're reevaluating the situation. So you take a really precise path down to the bottom. But if it's really, really, really small, then it'll take forever. And if it's too big, then you'll overstep where you want to go, and then you'll overstep on the way back, and you'll end up not really ever reaching the bottom. And so this is another one of these parameters that you're going to have to hand tune. So this alpha is something that you choose. If you see that your data set is huge and the bottom is wide, I don't even know how you'd see that, but this is the kind of thing that you could say, okay, I'll take a relatively large alpha, or if you have a lot of computing power and you don't mind, take a smaller alpha and take little tiny steps, and it'll be much more precise. Is that coherent? Yeah. Oh, and you keep running this, right? You keep redefining all your thetas and then taking a look again and seeing the direction of most change until every step really doesn't take you anywhere, right? Because once you reach the bottom of that little hill, your derivative will be 0, basically. And so these steps will get really small. And so once you see that this term, and you can set up a little if statement in your code, once you see that this term is like below 0.001, you could say, okay, stop running. You're good enough now. That's optimum.
So like gradient is like an arrow?
Yeah, it's an arrow that points, the gradient points in up the hill, and the steepest path up, and we're subtracting it.
So like the formula at the bottom is like changing the theta I, right?
Yeah.
You know, why do you want to like have all the data from the other thetas to like the one that's behind the subtraction? Isn't that like the summation of all the other
This right here?
other thetas?
Right, this is data, this is all, you're right, this is all of the predictions. So the thing that customizes each theta I, the thing that customizes the gradient for each theta I is this guy right here. This is the corresponding xi, right? So if this was theta 2, I would do all of the cost functions, each one times its x2, right? And that would optimize theta 2. And this particular method, I call this gradient descent. Technically, this is called batch gradient descent, where you look at all of the data, every step, right? You can imagine if this was like 1 billion houses, this might take forever. And there's other ways of doing it. Stochastic gradient descent is a different way of doing it. But in this case, the thing that customizes it for each particular theta is this x value out here. And again, we just got that right from the formula.
What's theta in that equation?
What?
Theta xj. What's theta there?
Theta is the parameters. It's how your algorithm decides what the price should be. So
theta I would be my
theta I, right? So it's going to be for each input, like let's say you have square footage and number of bedrooms. That's all you're talking about, right? So you have x0, which is 1, we're not going to worry about the intercept, x1, which is square footage, let's say, and x2, which is number of bedrooms. And so you tell the program, okay, here's the square footage and here's the number of bedrooms. And your program multiplies theta 1 times x1 and theta 2 times x2, right? So it'll take whatever theta is, it'll be a real number, multiplied by the square footage and the number of bedrooms, and it'll give you the price. And so I can't tell you what theta 1 and x1 will end up being. Theta 1 and theta 2 or whatever. I can't tell you what they'll end up being because this is what the program does. We don't have to worry about the slope of the line that it decides. And that's the point, right? We write the program for it to learn how to do it on its own, and then it builds the best slope possible. Yeah?
This is kind of getting into details, but I don't think you can reassign the thetas one at a time. I think you have to do them all at once, just because otherwise it would affect the cost function for the next reassignment. Because if you set theta I to some other number, then for theta I plus 1, the cost function calculation would be different.
Yeah, you have to do them from the old thetas.
Right, so you would either have to save the theta as another variable, or you'd have to set it to some temp value.
Yeah. Wonder how I would write that map. I think I would just put a sigma on the outside.
I think if you could just vectorize the whole thing.
What?
Theta I plus 1 equal to theta I minus that stuff.
Right. I mean, this is just, like, if you were to implement this, the way you would do that is you just, like, make an empty vector and fill all your changes of thetas into that empty vector and then add it at the end. I'm not sure that you can't update them live.
Live?
I mean, I'm not sure that you can't update them like this, cyclically, and just use the new theta in the calculation.
Oh yeah, no, that's not. Yeah, you're
Yeah, I'm
totally
pretty
right.
sure.
I think you can vectorize it though. You can just do them all at once.
Yeah.
Yeah.
that's
Anyway,
really-
again, specifics, right? The point is that this is, I'm not dismissing the question, but I'm saying, like,
Yeah, like I said, it's kind of
right, no, and that's great.
things.
And again, that's the kind of thing where if we were implementing this, and if we were, like, trying to look at each other's code, this is the kind of thing I might screw up. Because who the hell am I, right? So, what I like about this is just, I mean, this is operations that are algebra, multiplication, subtraction, addition, that you can code that will do this. This is now machine learning, and it's just math. So it's not like magic anymore. You don't have to type it in Python and just like have it happen. This is what's going on. Is that good? Does anything else on this slide not make sense? Does everything that's happened make marginal sense?
They just would be really dumb, but why can't you just solve when the derivative is equal to 0?
So this particular model, this particular algorithm and this particular linear regression model has an analytic solution. So yes, you could actually, for this one, you could solve it analytically. The only thing I will say about it is that the answer involves taking the inverse of an n by n matrix where n is the number of examples you have, and relatively computationally, if you have a huge number of examples, that might actually be more annoying than just doing this. What?
Are you talking about the normal equation?
The normal equation?
Yeah, isn't that what it's called?
I don't. I mean, I think it's like A, where A is, I guess, theta in this case is like x transpose x inverse y, something like that. Yes, this one has a analytic solution, but it might be more annoying to work out computationally than this. But again, most of the problems that we have are not going to have analytic solutions, right? Because these are really differential equations that we're estimating, and in particular, this one does have an analytic solution. Yeah. It didn't work.
Okay. Alright, so now that I've covertly installed all the things after they broke this morning while you guys were listening to Dale, I'm going to go
By the way,
through-
Dale is my name backwards. Feel free to call me Dale. It doesn't bother me at all. My name's technically odd. Huh? Whatever. Call me Dale. It's fine. It's easier to remember.
Alright, so this is the implementation of linear regression as we just described it with gradient descent in Python, so that's what we'll be using in the group. So I just wanted to, I'm not going to go through every single line, I can post it online if you guys want to go through every single line, but all I wanted to really say with this is like it's pretty chill, it's like not very difficult to do. So NumPy is a really popular library in Python. It just gives you a nice array object and all these nice vector operations. So you don't have to worry about that. And Pandas, the only thing I'm going to use that for is actually loading in the data into Python, and I'll never use it again. And PyLab is for graphing. So this is an extremely sort of low-tech, low-level implementation of, well, Dale wouldn't say so, but
That's how it would.
it is.
I don't like that.
Okay, so, whoa! Huh, okay. One sec. Ah! That gonna work? Okay, one sec, I gotta change kernel.
Does anybody here program in anything, like, does anybody here not program in Python and they're much more comfortable in another language? Just curious. Just what language?
Swift.
Just curious. If anybody else is C++. Anyone have any burning questions while we're waiting?
What's Jupyter?
That's the company that makes this thing I'm using. Yeah, this isn't a Python notebook.
I had no idea what you were talking about.
Python. Yeah, it's just like a thing where you could do nice things like this. Like, see, I have regular text mixed in here. So it's just to make stuff look nice. What's up?
Can we work along with you, like on our computers?
Sure.
On this one?
Sure, if you
Where's the
want.
link?
What?
Where's the link for this?
Oh crap, no you can't, I didn't put it up. So I guess you'll have to do it later. But I mean it's really not it's not crazy what's going on. So I'm importing the libraries, loading the data set in. So this is just a data set I found on a Google search. It's the first thing that came up. It's like not the best data set in the world, but a little bit of a spoiler, it won't even work that well. But it's the first thing I found, so you guys got a deal. So
It's just not a very linear data set.
couple things we're not going to worry about is there are algorithms and there are ways to use this information, the location, the well obviously we're not going to use that, the status, whatever. We're not going to worry about all that stuff because it's not numeric. So I'm just going to use, so you can see I dropped those columns. So I'm just going to use bedrooms, bathroom size. And we're predicting the price over here. Okay, this I'm extracting an array of this information from the pandas object, so that's the last you'll see of pandas, that's it. It's not important. And these are just for graphing. So here's what, God damn it! What's wrong? Oh, I gotta run these, I'm sorry. 1, 2, 3, 4, 5. No? There we go. Okay. So this is the, hey! This is the size and that's the price. So this is just a little one-dimensional picture of the image. Okay, let's make some variables. So this is basically me just splitting it into the training and testing set, like I mentioned earlier. The training set is what we're going to use to optimize our model, and the testing set is what we're going to use to evaluate it after we finished. So it's actually good practice to use a third set, but I won't because I don't care, and we'll get into why later, but I don't know why I even said that right now, honestly. Okay, so here we go. Okay, so this is kind of important. So we have those three features we have, the size of the house and the number of bedrooms and number of bathrooms. The number of bedrooms and bathrooms are going to be like 2, 3, 4, 5, and the size of the house is like in the thousands. So the reason that's going to be a problem is because you remember the parameter space? So you remember the graph of the cost function with respect to the thetas? That thing that we went down the hill on? So when we're going down the hill, we want it to be a relatively nice symmetrical hill, because if it's a long oval-shaped hill like this, we will end up jumping back and forth over the thing and missing it every time. And it's going to take us a while to get down. Does it make kind of intuitive sense? So what I'm doing is taking this long oval-shaped hill with this weird oversized feature, and I'm shrinking it down into a circle, and the way I'm doing that is I'm dividing every feature by basically its range. So I'm shrinking every feature down into 0, 1. So it's like, instead of saying, give me the square footage, I'm saying, how big is this house on a scale of 0 to 1? Does that make sense? No questions? Okay. So, and
Yeah.
here we go. Yeah.
What's going on in those 4 lines, in the last 4 lines of the previous bit of code?
Which one? This one?
Yeah, that little bit of Python. Just the syntax, what is that?
Okay.
And the selecting parts of the data.
Sure. Okay. So so the data is a big matrix.
Okay.
M, I'm just getting the number of examples. You can see that.
Right.
And this thing. Let me open up another notebook. So we get import NumPy. I really just can't see what I'm typing, and it's freaking me out. Then we can make an array object out of, let's say, 2, 2. So this is a nice 2x2 array. And what NumPy is really great at is indexing it. So here's A, right? And here is the first line of A, so it's using it as a list. And here is the whole first dimension of A and the first part of the second dimension. Does that make sense? Okay, I probably shouldn't have made it symmetrical like that, but
That makes sense.
Wait, so which part corresponds to the rows and which part corresponds to the columns?
okay, so basically when I'm indexing it, the thing before the comma is the rows, and the thing after the comma is the columns. So let me run that again just to make it clear. So here's the whole thing. Here's the row. So A0 is actually, oh man, this is so weird. Is actually the same as this, right? The 0 thing and everything. So they call it slicing because 0 is 0 this way, and the colon is slicing the whole thing. And this is 0 that way, and the colon is slicing the whole thing. Does that make sense to everyone? So that's all I'm doing. Back in the other notebook, which is over here, I'm taking, when there's a colon and nothing before it, that's a 0 back there, so I'm taking from 0 to 8/10 of the data set, and I'm putting that into the train variable, and I'm taking 8/10 of the labels and putting them into the label variable. Is that more clear? Everyone get it? Anyone not get it? Okay. All right. Moving on then. I think I already ran that. This is the scaling again, where I'm scaling them down to 0, 1. Okay. So here we go with our actual algorithm, and you can see. So ignore the plotting thing. That's just to make pictures. So you can see this is just exactly what we thought it would be. It's x dot theta plus b. That's our prediction. This is just to mess with the dimensions. Ignore that. The cost function is just the predicted thing minus the real one squared, and you take the mean of all that. So this is literally the math that we wrote. We're just typing it in as is. So this is very clear what's going on. This is taking the gradient like we described earlier. Any questions on this part? Cool. So, okay. That is the plotting part. Don't worry about that. Okay, so let's just plot a random one. See how that looks. So I initialized a random theta, and so theta, there's 3 things. There's 3 coefficients for the 3 features. So each coefficient is the slope of that feature. Does that make sense? So you can see there's 3 random slopes, 3 random b's. So this is how we're going to be sort of looking at it. So, all right, is that clear? Okay, and now time to actually train the model. Now that we have all the, it's sort of like we had the slide where we made all the definitions and then we talked about how to actually use them. So that was all the definitions. And here we go with this function. We'll actually go down the hill and optimize the cost function. So should I talk about what's going on in there, or is it clear to everyone and you want to just kind of, what do you guys think? Vote for the first option, going through this line by line. Vote for the second option, just kind of looking it over and moving on. 1, 2. First guys win. Okay. All right. So this thing, I'm just going to be storing the cost over time, so I can see if how I'm doing. Later on, I'm going to graph it. Okay, so this is clear. We loop until the gradient is close to 0, unless we hit the. Oh man, my screen is wider than this screen.
Maximum number of iterations.
Yeah, max iterations.
You don't want it to run forever.
So we pass that. Yeah, we don't want to keep going forever. So here's the break statement if we hit the maximum number, and here's the break statement. I should have probably put them next to each other, but what this will do is I'm finding the maximum gradient of the four sort of directional derivatives, and I'm making sure that it's really small. So if the maximum gradient's really small, that means all of them are really small. That means we're at a kind of a flat spot, so it's time to stop. Does that make sense? Okay, and while we're not stopping, what we're doing is getting the cost, saving it, calculating the gradient, and updating our parameters to be a little bit more in the direction of the gradient. And the a little bit in that statement is represented by this alpha, which, as Dale mentioned, is a learning rate. That's pretty much it. Everything clear? Any lines that you guys don't get? So this is just once in a while I'll print out what's going on. That's all that is. Cool. Okay. Yeah.
Is there a name for the cost function we're using?
Is there?
Least squares error.
Yeah, ordinary least squares error. Kind of the. Okay, and we're returning the finished model and our history of what happened with the cost. Okay, time to run it. So here we go. This is going to print a lot of stuff. So I'm going to collapse it. Oh, there we go. So you can see it starts off totally random, and then it sort of comes in closer and closer to something that sort of looks like it represents the data set. You guys see that? So that's pretty much the whole point, is for it to do that. So it's still going right now. We're going to give it a minute. Or should we just stay at the bottom? Just gotta keep dragging it down. that first one's really not doing well.
Looks like the third one is stuck.
Max iteration is reached. Which one? This one?
Yeah, I don't see it moving.
Yeah, well, it probably hit its where it wanted to be. I really don't like that though. I guess we just didn't wait long enough. I'm not gonna rerun it though. Whatever. This is implemented by me, and you guys are gonna have to deal with that. So here is. Whoa. Okay. All right. Something's wrong. Oh man, what the hell? Anyone see anything wrong?
Maybe it's so good at learning the curve.
Ah, I'm gonna run everything again. If this doesn't work, I'm sorry, but you guys are just gonna have to believe that I'm smart.
I mean, we know that it's getting a lot.
It's doing something. I mean, if it's doing something, that's already like pretty good. You know what I mean? Hey, it's staying at the bottom. Okay. That looks kind of nice.
The animation?
Yeah, see it kind of moving up. It's not even an animation. It's just.
No, well, it kind of is.
It
Isn't
is.
Showing pictures in a row.
That's the slideshow.
By the way, these do, like, if you write an algorithm and you run it and your computer just doesn't say anything for like 5 or 6 minutes and then it pops out a result, I mean, you should probably have it print updates like this, but these algorithms can take a long time.
Yeah.
Especially when you start, like, you know, you get a huge data set and you're doing like 2 or 3 or 4 or 5, 6 different algorithms on it. You know, you read like people who win these competitions and they're like, oh yeah, my algorithm took 22 hours to run on my 7 GPUs, and you're like, oh crap.
Okay, so I guess the cost started really small or something. But let's see. Started out with a 0.7. We got down to 0.014. Wait, that's
No.
not the cost.
0.002.
0.002, that's great. What the hell? So why is it showing me? What? Oh, okay. It might just be like a bad scale. So
No, it's showing it to you correctly. Look at the graph at the bottom. Anyway, it doesn't matter.
no, I'm just gonna do the first 3,000 just to see. This will be my last attempt at
300.
redeeming myself here. I promise. Okay, there you go. So you saw it go
Right.
down. It just went down really quick.
Big man.
So that was our cost function. Does that make sense to everyone? Why it's doing that? That's what we want. So, yeah, well, it didn't do that the first time I ran it, by the way. I had to go back and mess with it, but there you go. Moving on. Looks pretty good. So now we're going to check it on the test set. And this is the root mean square error. So this is approximately about how much money we're going to be missing it by. This is a lot of money. So this is a very simple model. I did not say it was going to be a good model. I said it was going to be a simple model. So if you predict your actual housing prices by this model, then it sucks to be you. But this is
Plus or
basically
minus
what came out.
$250,000.
Okay.
Big man.
And let's compare it to the pros. I did not finish implementing this, which is fine because they implemented it for me. But what happened was my scikit-learn broke, so I tried to fix it while Dale was talking. We'll see if it worked. But scikit-learn, it's the guys that made that picture I showed you earlier with the big flowchart. So they implemented all these algorithms really nicely, a lot nicer than me. So let's see how they did, and it's not going to run, so you guys do it on your own time. Congratulations, I did it. Okay. Leave page.
Leave page.
That's it. No more of that. Okay. So that's the implementation.
Question.
Yeah.
Why do we plot learning curves? What are they useful for?
What learning curves? Oh, are you talking about the cost function over time? Okay, so like I said before, the first time I ran it, the cost function was going up. So, well, it wasn't even going up. It was starting really low and then shooting up. And obviously I wasn't happy with that. So the learning curve really gives you an idea of what's going wrong with your algorithm. So one of the things that's good for is optimizing what's called hyperparameters. In our case, alpha, the learning rate, was a hyperparameter. That means it is a parameter that our model depends on, but the machine's not gonna learn it. We have to set that parameter. Does that make sense? So the learning curve is good for sort of deciding on the types of things that the machine can't decide on its own. Cool? Okay. Okay, so that was a simple model, but actually linear regression does pretty well if you kind of fake it out. The way you can do that is you can make a more complicated model by making more complicated features than plugging it into a simple model. So if we had one feature over here, and then we had another feature which was just that squared, and another feature which is that times another feature, we could potentially generate infinity features, right? And what happens when you do that is you can make a really complicated model that fits all of your data perfectly. And that actually is a terrible idea, as you can see by this picture. So this is a degree 15 polynomial. It's a complicated polynomial. And it's hitting almost all of the data points exactly, even though these really could be modeled well by just a line. Do you guys see that? So this is doing some crazy stuff that is not at all true about the data. Like these, you know, stuff like that. So that's called overfitting, which is the title of the next slide. Who knew? So this is overfitting. What that means is that it fits your particular set really, really well. But if you show it new data that's from the same place, it probably won't fit because you really over-optimized it for your specific thing, and you basically fit the noise of your set instead of the signal. Does that make sense? Yes? Clear? So underfitting, your model's not complicated enough. So you could tell you're underfitting if your error on the training set's really high. And you can tell you're overfitting if your error on the training set is very low, but your test error is very high. So data you haven't seen before is hard for you to handle. So for that reason, like I mentioned earlier, I just said those two things. It's good practice to use a cross-validation set. So if you just have a training and a test set, and you make your thing do the training set really well and the test set really well by optimizing your learning rates and hyperparameters and stuff like that, the model has fit your training set, but you personally have fit it to the test set, right? So it's not entirely fair. Do you guys see what I'm saying? So that's why you're supposed to do your hyperparameters on a third set called the cross-validation set, and then save the test set for the very end for your published error rate results. Is that clear? Okay. I'm gonna just don't pay too much attention to this. This is just another extension of linear regression. So we just did regression. This would be the classification version of the same model. Yeah, I won't talk about it. Okay, so there's a lot of algorithms out there. It's a little freaky. There's a lot of them are extensions of that basic idea. A lot of them aren't. So, you know, this was just a basic introduction to the most basic algorithm. And really the purpose was to open the door for you guys to be able to read about these other ones now that you know sort of these terms and what's going on and what a cost function is. So this is a huge field and it's worth sort of investing your time in, at least in my opinion. And that's about it. Does anyone have questions or things like that, or no? Feedback?
Can you post the PowerPoint online?
Sure.
You said post the PowerPoint online.
I said sure.
Oh, I thought you said, are you sure? That's not an appropriate response.
I did kind of mean that, but.
Does everyone know what we like? What the Kaggle? Does everyone know about Kaggle? Does that sound familiar? That we want to play with those and practice on those, maybe compete in those? No? Maybe? Anybody? One person doesn't know. It's cool. It's basically, it's a website where companies or independent groups or whatever post machine learning problems that they don't want to solve, and then they offer rewards. And so there are ones that are already up there that answers are known for, that are just for knowledge, for practice, and highly recommend those, especially the Titanic one, because it has a walkthrough if you want to follow it in Python. But there's companies that are basically saying like, hey, if you can do this for us, we'll give you whatever, 15 grand. Like obviously, there are people who win most of these, and then there are people who don't win many of them. But it would just be, it's a problem that's real in the world, that people are interested in, that they want solved, and there's a bunch of them in one space, so we can pick ones that we're interested in and all do them and share code and
that's actually kind of the plan for the group. So if anyone doesn't know, I know a lot of you are here from the group, some of you just know it from the Facebook group, but basically the idea is we're going to meet up, we're going to split into groups, decide on like approaches. There's different like approaches, different fields and stuff, and we are going to try to tackle one of those sort of public problems and see how well we can do. And hopefully, we'll do okay, and maybe we'll do another one afterwards. But that's kind of the idea. So I guess I don't know if we'll be doing it at this time. It depends who decides to stay in the group, who decides this was boring, they want to leave, and it depends when everyone's available. But basically, yeah, I guess we'll meet up next week. And another thing we might do, which I just thought of just now, but it seems like a good idea, is post a bunch of like sort of further resources, like maybe like tutorials, stuff like that. Should I keep talking? Is there any questions? Are we good? We're good?
if you haven't participated in the doodle poll, it's the best way we have right now to see when people are open. If you're like, doodle, what's a doodle poll? Go to the Facebook group and look for the post about the doodle poll, so you can mark when you're free during the week. Because if you don't participate in that, we don't know when you're free during the week, and we won't schedule with you at 9.
Dale worked very hard on the doodle poll, and he
Day and night.
He gets very emotional. He gets very emotional about the doodle poll.
Yeah, that's right. If you don't participate, I'll send you an email with like sad words in it. I won't do that. I'm not gonna. No. Wait.
You can write up an email.
Wait, so that,
And look, I'm not gonna do that. I don't care. I'm not your mom. You participate if you want to participate, or not, go home. That's fine.
Yeah. Well, what will actually happen if you don't participate is we're going to make it a time that's bad for you. Not on purpose, just
Purpose.
on problem.
I'm gonna find you. I'm gonna find your schedule during all of your classes. Like mandatory meetings during your classes.